Hi guys, and welcome back to what really is the last video of the Big Idea 2 note set 4 on gas laws. We're going to be talking about the ideal gas law and real versus ideal gas laws. So, we are starting down on page 5 with the ideal gas law. So, the ideal gas law describes a single gas. So, basically, they had all of these observations of all of these properties. And they realized that they all follow the same relationships, okay? And it depends on what you're holding constant. So when you hold the number of gas laws constant and the temperature, you end up with this is a constant, and so volume over pressure, which is Boyle's law, okay? It also shows the direct relationship that is Charles's law and Avogadro's law, each held with distant constants. The important thing to note for the ideal gas law is that, one, it's only useful at low pressures and high temperatures, aka when gases act like ideal gases and follow that kinetic molecular theory we talked about earlier. But it's for when you're only describing a single sample of a gas. It's not when it's changing volume or changing temperature. Though you can still use it for that. That's why this equation is the only one that shows up on your gas laws sheet. Okay? It's in the gases, liquids, and solutions on the back of your equation sheet. So, you don't need to memorize this because guess what? It is also written on your equation sheet. But P is pressure. Hey, what's V? Volume. What is N? Number of moles. R is the new one. So R is what unifies all of these things. We call it the gas constant, okay? There are there's a million different ways you can use the gas law, but 3 of them are on your equation sheet, so there are 3 of them that you need to know how to use. The only difference between them is the units, okay? So it's the same constant, just in different units. This 8.314, this one we call the energy gas constant because it has J in it. J is for joules, which is a unit of energy, okay? So it's how many joules per mole Kelvin, okay? Again, remembering that they use this weird little negative thing instead of doing joules over moles times Kelvin. It's just what they do. It is 0.0821 in liters and atmospheres per mole Kelvin, and it is 62.36 when you're using torr. Okay, so anytime that you're using one of the gas constants, make sure that your other variables, your other units in the equation match up with the gas law constant that you're using. Oh yeah, and T is temperature. Notice that the temperature is always in Kelvin, okay? We have to use Kelvin. The negative numbers in Celsius just mess up this scale, so we need to use that absolute temperature scale. Okay, now you can actually rearrange the ideal gas law to solve for the density of a gas or the molar mass. Remember how density is mass per volume, okay? Mass over volume. How we use this is we relate the mass to N, the number of moles, okay? So the mass, you can think of the mass as the number of moles multiplied by the molar mass, okay? Sometimes you'll see it as just a solo capital M for molar mass. Sometimes you'll see it as MM. I prefer MM, so I'm going to mostly use that when we do this, okay? MM, molar mass, okay? Small m is just mass. And N, remember, is the number of moles. This right here is the molar mass, okay? So if we sub that in for the V and the N, okay, we substitute N and the N, it works out. You can solve for the density of a gas. Okay, so again, like I said, the density of a gas you can think of as the mass over volume. It is the mass over volume. In terms of the ideal gas law, when we're talking about gases, you can use pressure multiplied by the molar mass over RT. Okay, and I could show you all the derivations of that. If you're really concerned about it, go ahead and try to solve it out for yourself using this equation. I'm sure you can get it, or I can always show you in class. Okay, For molar mass, there's a little trick to remember this one, okay? The molar mass of a gas, okay, it's called the molar mass kitty cat, okay? Because he puts dirt over his P, okay? The D being density, R being the gas constant, T temperature, and P being pressure, okay? But, yeah, remember the kitty cat. Okay, because look, it's a kitty cat. Those are his weird ears. Yeah, that makes sense, right? Okay, but all good cats put dirt over their pee. That is the molar mass kitty cat, and it is a shortcut to remembering how to use the ideal gas law to solve for molar mass. Okay, so let's go ahead and do some practice with the ideal gas law. Okay, keep all these equations in your mind. Make sure you got them written down, and let's go over it. Okay. A sample of hydrogen gas has a volume of 8.56 liters at a temperature of 0 degrees Celsius, which is 273 Kelvin, okay, and a pressure of 1.5 atmospheres. Calculate the number of moles present of H2 in this gas sample. Okay, so this is a basic perv-nert equation. PV equals nRT. Okay, the R that we need to use in this case, we're working with atmospheres, Kelvin, and liters. So that is going to be the 0.08206 liter atmospheres per mole Kelvin gas constant. Okay. This is the only time that I'm going to actually use those units just so I can show you how they work out. Otherwise, just don't worry about writing them. Make sure you add them in at the end, okay? As long as you're using the right gas constant, you will be fine. Okay, so pressure, 1.5 atmospheres times volume, 8.56 liters equals N, which we don't know, that's what we're looking for, times R, 0.08 206 liter atmosphere per mole Kelvin times temperature, sorry I'm running out of room here, 273 K. Okay, so then we move those over and divide the R and the T. Can I just move these? Will it let me? No. No, it won't. Okay, so write them back down over here, 0.08206 liter atmospheres per mole Kelvin divided by 273 Kelvin. Yep, divided on that side so that it cancels out. Now let me just show you how these units work out real quick. The liters on top cancel out with the liters on the bottom. Atmosphere on top cancels out with the atmosphere on the bottom. And then we got Kelvin canceling off with Kelvin. Therefore, we have mole on the bottom of the bottom. Remember, when you divide by a fraction, it flips upward. So the units that we are left with is moles, which is cool because that is the units for N. So now we got to plug that all into the calculator. So I'm going to just use parentheses and do 1.5 times 8.56, close parentheses, divided by 0.08206 times 273, close parentheses. And you get a value of, I'm out of room to write, so using a different color, N equals 0. My pressure only had 2 sig figs, so I'm limited by that one. So I'm going to put 5.7 moles. Okay, go ahead and double check my answer and make sure I'm right. Okay, cool? Okay, cool. So let's try the next one. This one has to do with density. The density of a gas was measured at 1.50 atmosphere. Okay, that's pressure. And temperature is 27 degrees Celsius. Make sure to convert it to Kelvin. And the density is 1.95 grams per liter. And you're going to find the molar mass. Okay, so the equation that we're using, remember, is going to be density equals, scroll up and look real quick. Oh, I didn't put it there. Okay, density equals pressure times molar mass over RT. Okay, go ahead and plug it in, see if you can find it. Okay, so I got a molar mass of 32.00 grams per mole. So maybe it's sulfur gas. Yeah, I don't know. But yeah, go ahead and double check. Make sure I got the right answer. And make sure you're using the right R. You should be using the R with liters and atmospheres. Okay? Okay, cool? Okay, cool. So I want to show you guys something. Use the ideal gas law, Pervnert, to solve for the volume of 1 mole of gas, so N is 1 mole, at STP. Okay, remember STP is a temperature of 273 K and a pressure of 1 atmosphere. Okay, so again, the R that we're using is the atmosphere one, 0.08206, and I want to know the volume. Okay, let's plug it in. So 1 times volume equals N, which is 1 times 0.08206 times 273. .4 liters. Does that number seem familiar? It should. You learned this back in stoichiometry. Okay, this is the molar volume of a gas. 22.4 liters is how much any 1 mole of a gas, doesn't matter what gas it is, if it's acting ideal, 1 mole of a gas will have a volume of 22.4 liters. That's just how the ideal gas law works out at STP. So this is a shortcut to solving a lot of problems. Okay, like a sample of nitrogen gas has a volume of 1.75 liters at STP. So we know at STP, every 22.4 liters is 1 mole. Okay, liters and liters cancel out, and we get 1.75 divided by 22.4. We get 0.077 moles of N2. Okay, and just to prove this to you guys, I want to plug it into Pervnert real quick. Okay, Pervnert, PV equals nRT. Okay, the pressure at STP is 1, volume 1.75 equals N, that's what we're trying to find, R 0.08206, and temperature STP is 273 Kelvin. Okay, when you solve for N, 1.75 divided by 0.08206 times 273, what do ya know? I get 0.078. Okay, little off, probably just a rounding error, but you guys get the idea. Okay, this is a shortcut. You can use it anytime a gas is at STP. Okay, so we have a couple other vocab terms I want to go over real quick. Mixing of gases is called diffusion. Okay, diffusion, think whoever smelt it, dealt it. Okay, if someone farts next to you, they're going to smell it first because it's going to spread out and mix with the other gases in the room close to them. Okay, effusion is a little bit different. You can also think of whoever smelt it, dealt it for effusion. Effusion is the passage of the gas through a little pinhole. Okay, so it's the speed at which a gas will transfer and spread out. Okay, so 2 other terms you might think of. Now I want you to think for a second. Will a gas with a small molar mass, like helium, will that move faster or effuse faster or slower than a large gas, like uranium hexafluoride, UH6? That's a really large gas. Which one will effuse or move faster? What do you think? Okay, the correct answer there is, of course, the smaller one, okay? Helium. Okay, one, it's smaller, and remember we were talking about the speeds of a gas, okay? At the same temperature, it's still going to move faster. it is smaller, so it moves faster. It's going to move faster through a pinhole. It's going to move faster to the tube. Any of that. Okay? So, last thing we need to talk about with gases is, guess what? You know all these equations? They're only for ideal gases. Most gases are not ideal. But they can be, okay? At low temperatures and high pressures, that's when they get far away from being liquids. But most gases we can treat as ideal gases. Okay? If the molecules are close together, they're going to interact with each other. That's what's going to cause the deviation. But we can ignore it for the most part. There is an advanced form of the ideal gas law equation. Okay? It looks like this. Okay? A and N are just, or A and B are just constants. But you can see it subtracts the volumes of the molecules from the volume and adds some pressure due to the molecules interacting. You don't need to be able to understand this, okay? You just need to know that, when gases are closer together and when they're bigger, they deviate more from ideal gas law, okay? They like showing these graphs of it, okay? So here it shows an ideal gas, PV over nRT should be a constant, okay? It should be the same all the time. But you can see at high pressures, okay, these gases go further away from the ideal gases at, again, the high pressures. They're deviating from this perfect ideal relationship. Okay, but they're close to it down here at the low pressures. Okay, they cross it somewhere in like a medium pressure where the pressure is balanced, but then they deviate more from it the higher the pressure goes. Okay, same here. You can look at different temperatures. Okay, an ideal gas law, PV over nRT should be a constant. Okay, but at different temperatures, the higher the pressure goes, it's gonna get a little off. Okay, the higher the pressure, the more the deviation. High temperatures has less deviation. The lower the temperature, okay, 203 versus 673, the less deviation. Okay, so good to know. Okay, cool. That's all we need to know about gases. Okay, cool. Now go do your homework.